Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept in calculus. Of course, this is the concept of differentiation rules. So this is differentiation rules. And basically when we talk about the concept of differentiation, of course in our video of introduction to calculus, we said that calculus can be divided into two broader topics. That is the differential and the integral calculus. So for this case, this concept of differentiation rules is going to fall under the concept of differentiation. And we're going to look at some specific rules which are going to assist us in trying to find out how we can be able to do a differentiation of functions. So the first one we're going to look at is power rules. It's a power rule. And next we'll look at constant multiple rules, or just constant multiple rule. Then next we'll look at the concept of the sum or difference rule. And basically we're also going to look at the power rule for positive integers. Of course, in this category of power rule, we are going to expand it somehow in order to try and explain the concept of power rule for positive integers, and also for the constant function. We are going to look at some of the areas in which, so mainly we are going to discuss about this specific thing, but in any case we come across or maybe we find time, we just have to add an additional one. So in this case, this will be our main areas of concern. So as we defined the concept of an integral, so we're going to also look at the concept of a derivative. And that is to do with the derivative of a function. And we're going to do an illustration using a graphical representation. So in that case, I will just have an illustration on the board to try to give the concept of an integral. So basically, when we have a graph for the x and y variables represented as such, we can be able to give any particular point on this xy coordinates, bearing in mind that that's the point of origin, by just giving a reference of the x and y axis. Perhaps if this is point P and Q, we can give the extent to which this particular point stretches along the x-axis and the height at which it stretches along the y-axis by giving its coordinates as x and y. So respectively, for point Q, we can be able to give it is a stretch along the x and y intercept by giving it the extent to which it stretches along the x and y intercept. So this will be x minus, perhaps if this is m. So in that case, of course, we are going to see that, or perhaps if I give it as x1, y1, those will be its coordinates, and the stretches along the x and y axis is given as such. Now, suppose we have a function that is represented on this xy coordinates. This is y, x, that moves along that direction. Then we can be able to find what we call a derivative by trying to find maybe if this is a distance against time, then we can be able to find what we call a derivative, or the rate of change of distance. Distance is given as s and time in t. We can be able to find the rate of change of s over the rate of time, change of time given as such. So therefore, this basically is referred to as the gradient. And it refers to the change in the y-axis against the change in x-axis, which is represented as such. So therefore, this one can be regarded, so maybe that's from point P to Q. This one can be regarded as a derivative, or maybe the derivative of a distance with respect to time. So sometimes we are going to write it as the change in s over, okay, just give it some space somewhere. So this is q. So the change in s over change in t, which we have referred to as a rate, is going to be given as ds over dt, which basically from the physical quantities or the motion in a two-dimensional space or motion, linear motion, we refer to that one as velocity. So therefore, this concept of a derivative is going to give us some of the ways in which we are going to represent physical quantities. And basically from this we are going to see that we can as well refer to as this differential aspect of this particular phenomenon as a derivative. So therefore, if we try to look at these specific rules which are being regarded as the differentiation rules, we're going to see a particular relationship in that I can be able to refer to that one as ds over dt as a, which is representing v as a derivative of s. So therefore we're going to see this particular function representing a derivative whereby in some cases it's going to be represented as a function of f with respect to t. I don't know whether that is. Let me just leave that one for now. I just first of all go to the graphical representation, and then we will go into other details which are going to give us. So let's try to have a representation of this particular graph, and then we have, this is point O, this is a point, this is x and y intercept, axis, and this is a function. So in this case, y can be represented as a function of x, and we're going to see why that one is the case. So in this case, we can try to see if from our graphs of displacement, time, velocity, such a kind of a behavior whereby we have a particular variable which, a particular function which is not changing with respect to x, then we're going to refer to that one as a constant. So basically it refers to the fact that the change or the difference in this y-axis, which we can denote as h, does not change with respect to the x variable. So in this case we can be able to denote this constant as c, and therefore if at a particular point, perhaps x, we give the coordinates for this specific point at this junction, and it will be x, while the y-axis is given as c. But if there is a slight change in the x-axis, perhaps we give it as there's a change by m, the distance m, to this particular point, then we're going to give the value for x at this point as x plus m, and then the coordinate for this is x plus m c. So therefore we can see it's only the x-axis that is trying to change. So from the concept of a derivative that are given using these graphs for which are demonstrated of the one that we are normally used for distance against time, we'll only have a gradient if there is a change in y over change in x. So this gradient, which is ds over dt, is given as, so this is s against time. So it's given as change in y over change in x. So if the resulting change in the y-axis is 0, so mathematically any quantity that is which as a numerator 0 is going to be 0. So therefore the change for that one is going to be 0. therefore denoting that this y is a constant, which is c, which had of course given an illustration at that particular point. Now generally, you can just do away with this, like this one. So this was y is equals c. So generally, if we have c as a constant, then we can have the derivative for c with respect to time given as, or maybe the change. Now that we have the x and y axis, the change in the y axis with respect to the change in x being given as 0. So therefore our derivative for that kind of an expression is 0. So this one denotes that trying to find the derivative of this particular function that we regard as a constant will just give us 0. So therefore generally we can say that the derivative of every constant function that is given as c will be equals to 0. And we're going to see that one using maybe specific examples. So that's the first rule of differentiation that we have been trying to discuss by merging it with the concept of a derivative that I've talked about. So therefore the derivative of a constant equals 0, as I've generally explained in that specific part. So we just move on now faster to rule number 2, since the others will have depended on this particular explanation. So we'll go faster and try to find the other rules. So number 2, we have what we call the power rule. This is the power rule for positive integers. So the integers, I hope we talked about the concept of numbers in one of our videos, so we can just have a check over what integers, rational numbers, etc. are. So this is if n is a positive integer, if n is a positive integer, then we can be able to represent its derivative as d over dx. So the derivative with respect to x of x exponent n will be given as nx n minus 1. So therefore, if n is a positive integer, so we'll take note of this particular intentional mention of the term positive, so that there is another way in which we're going to represent negative terms in that case. So if n is a positive integer, then its derivative will be given using this particular equation. And then we have rule number 3, which regards the constant multiple rule. Constant multiple rule. And in that constant multiple rule, we have functions which were, of course, a function whose derivative can be able to be calculated is known as a differentiable function. And if a function, maybe u is a differentiable function of x and c is a constant, therefore we just put it in the form of a statement. If a function u is a differentiable function of x and c is a constant, then its derivative, which is given as d over dx of a function with that constant, will be given as the constant times the derivative of that specific function. Now this case, of course, will apply to the power rule that we have already discussed, in that it will take the differential part of this particular function and apply as the power rule. Therefore, if we had a function like, because I'm just going to use this space here, so therefore I just have this one as such. So suppose we have a function like d over dx of c x to power n. Its derivative will be given as cn x n minus 1. So you can see still this is a merge of the power rule together with the constant multiple rule, which is trying to define a differential, maybe a derivative of a function which encompasses these two specific aspects. So that is in regard to the constant multiple rule. Now there are some special cases whereby we find that the derivative of a negative of a differentiable function is the negative of the function's derivative. And this has already been discussed, as we said, about the rule in number 2. And I'm going to give this one by demonstration. So for extension of rule number 3 that I've discussed, I'm just going to give another special case for rule number 3. So this is rule 3. I'm going to give a special case in this case, whereby the derivative of a negative of a differentiable function is the negative of the function's derivative. Now in this case, we're going to see that if we have d over dx of a function which is negative, then we're going to have d over dx negative of that particular function, which of course is we're going to treat that one as a constant, and therefore it's going to be negative 1 d over dx of this function u, which of course from this specific rule number 3 we have defined it as negative du over dx. So therefore this is an extension of rule number 3, whereby we are discussing about the concept of a positive integer. So maybe if this function is a negative 1, therefore we're going to treat it as such, and trying to do a substitution for this as a constant and treat it using the rule number 3, and therefore its derivative will be a negative represented as that. So then lastly, we're going to look at the sum rule for derivatives, and that is rule number 4. So rule number 4. We're going to look at the sum rule. Now this is going to basically entail the concept of the sum and difference, and these rules of differentiation. So this is number 4. The sum rule. What will be the derivative of maybe two functions? Now for instance, if we have u and v, which are differentiable functions of x, so u and v are differentiable functions of x, then the sum, which is given as u plus v, will be differentiable at every point where both u and v are differentiable. So this statement defines the concept of the sum, and we're going to see that the derivative of the sum of two functions, that is u and v, which are differentiable, will be the sum of the derivatives of those functions. Now this one can be illustrated using the concept of derivative that we have mentioned, whereby this is going to be du dx plus dv over dx. So basically that is what it refers to. And we're also going to see which specific rule is going to apply on maybe the difference of those specific functions. As we have mentioned, the 4 rules of differentiation, it's of essence for us to try and find out how we can be able to do an application of these specific rules. And in our next video, I'm going to use maybe a demonstration of some specific functions in trying to show how some of these rules, of course, can be applied. So in that case, we're going to look at in our next video about the constant function rule, and the constant function rule and the power function rule, specifically using graphical representation, and try to see how those specific graphs behave. So in any case, these are some of the specific rules that we're going to use in differentiation. Of course, we have done a video on the integration, simple integration rules, and we're going to see that the concept between the two now is going to be advanced maybe further for other specific functions that we are going to discuss in other videos. So of course, we cannot just mention them for now. We're just going to restrict ourselves to these specific rules in this video. So that is it for today, guys. I hope that these rules are going to be, of course, of essence to us, applicable in different scenarios that we're going to encounter the concept of differentiation. And in any case, if we come across the two for differentiation and maybe integration, then we can be able to understand how we can be able to handle them. So for that case, thank you. Bye. God bless.